So let's just do a quick recap. Age, weight. So you get a baby elephant or whatever it is, and you measure its age from the day it was born, 1 month, 2 month, 3 month, 4 month, whatever. And then its weight. And each one of these dots are a particular elephant, you know, whatever its age was and whatever its weight. And we call that diagram, right? We call that a scatter plot. And we introduce terms that we use to describe scatter plots. I put, this is just me, you won't find this probably in any YouTube video, but it helps me visually. I tend to put a little sausage skin around the thing, just to emphasize it. Would you agree this is positive association because it's going uphill? Great. So we would say it has a positive association. And that kind of makes sense. Wouldn't you expect an older elephant to weigh more than a younger elephant, right? You know, as you get older, you get heavier, but up to a point. Positive. Didn't we also introduce a strong, moderate, and a weak? Right. And that's a little bit more subjective, isn't it? Because what you think strong, someone else might think moderate. I would probably go moderate on this one. You might disagree with me a little bit, and I can understand that if you did. I think we'd all agree it's not strong. Would you agree it's not strong? Strong would be basically all the dots would probably be inside that pen, right? There'd be a little bit of bumping up and down, but there'd be a very skinny sausage, right? Would be an example of strong. You might think it's weak. I think it's moderate. We also introduced the words linear, and God, I didn't even remember this word. Is it curvilinear? God, what is it? Yeah, weird word. I don't like it. I mean, you should just call it curved, right? But, well, anyway. In this data set, would you agree that it's probably linear? Right. If it was curvilinear, wouldn't there be a kind of bend to it, for want of a better word? Good. And the last thing we talked about, so I guess I'll put bubbles around each of these. And the last thing we talked about is outliers. Would you agree that this particular scatter plot doesn't have any distinct outliers to it? Can we pretend, just for argument's sake, that was a guy up there? Then that red guy would be an outlier, wouldn't he? And that's kind of what we got to, I think. We did do, if I gave you a story, would you expect that to be a positive or negative association? So if I went and said, number of miles traveled in your car and how much gas that you have used, would you agree that would probably be a positive association, right? The further you travel, the more gas, you know, petrol, whatever you want to call it, you use up. And we did something like that. So is there any questions about that? Or we feel pretty comfortable that, you know, we've grasped the namings that we use and what scatter plots look like?
I have a question about, are there any, for the strong, moderate, and weak, like, are there any brackets on that? Like, is there any way to actually determine it so it's not a personal opinion?
There is going to be a thing called the correlation coefficient that we'll discover later. And the correlation coefficient is a number between 1 and -1. And if you're really close to 1 or really close to -1, then you're strong. There's no agreed standard on that. But if you wanted a standard, you could create one and say, if you're between 0.9 and 1, you're strong. If you're between 0.7 and 0.9, you're moderate. If you're between 0.4 and 0.7, you're weak. And if you're less than 0.4, you've probably got no association at all anyway. right? So there isn't one that I know of. Now, that doesn't mean maybe the Statistical Society of America got together and made, ranges that would fit those words, but I don't think they have. So it's a little bit more precise because at least you've got a number now. It'll have an R value of 0.2, which is virtually nothing going on there, right? Or an R value of 0.9, which is very strong. At least you've got that. And you can also then compare two scatter plots. If I have one scatter plot for males and it's 0.9, and I have it for females and it's only 0.5, then I can be pretty sure that the association is very strong for the males, whatever the variables are. But for the females, it's pretty moderate to weak. So you could use it a little bit for that. But nothing very precise. So there's a lot of judgment calls, which is why I tend to avoid questions like that in the test, because there's too much judgment in it. Okay, any other questions? Okay, let's have a look at the homework questions. Oh, by the way, did you hear my dog barking in the background? That is Bailey. Bailey is as thick as two bricks. He is probably barking to tell me that a leaf went by. Basically, he is a very protective dog, and he believes that his job is to tell me when something's going on around the house. So dogs going by, people, leaves, doesn't really matter to him. He comes and tells us. Not a very bright dog. Okay, here we go. Here is some data. God, it's a big table. This particular one is cities in America and their latitude and the average temperature in August. Okay. Now you could do latitude along the x-axis because that's the first thing. And the y-axis, you could do the temperature. And you can imagine you could plot the point 26,83 and it'd take you about half an hour and you'd get it. But wouldn't it be nice if we could just let technology do it for us? So let's show you a scatter plot. I'm going to use salt. Oops, move this out of the way. Are you seeing, I hope, the same data again? See it here? Can you see? Yeah, okay. Now, I want a chart, so I'm clicking on that. I want a scatter plot, so I click on that. And the x-axis was going to be latitude, and the y-axis was going to be August temperature. And I'm going to shrink this up a little bit so we can see it. I don't know, one more maybe? Yeah, okay. Can you see along the bottom is latitude, vertically is the August temperature. Do you see this line that they've got here? Just kind of interesting, right? It's called the regression line. It's actually, basically it's the best fitting straight line through it. But let's get that out of the way so that we can just see the scatter plots. And I try and move that up just a touch. There we go. Now they're going to ask some questions on that, but let me make up my own before we look at what their questions are. Would you agree that this data is negative association? Would you agree that it's at least pointing downhill? So what that means is as the latitude gets bigger, the average temperature in August gets less. Do you know latitude is how far north you are of the equator? So that kind of makes sense, right? The further north you pick a city, isn't it probably not going to be as warm in August? Right? And now, what else can we ask? Would you say, you have to commit yourself to one or the other. So the choices are curved or linear. Would you say this is linear or curved? What's your best guess? What do you think? Curvilinear or just linear? I'm going to go linear, right? It's not great data. Do you know, I would say that this one here is probably, it's either moderate or probably more likely weak. Do you agree? If you do a test question, you know, when I give you a test and you want to cover yourself, couldn't you say things like moderately weak, which is kind of somewhere between the two? And you could use moderately strong, right? So that kind of gives you 5 names now. So you've got a little bit more flexibility. If you're not 100% sure it's strong or moderate, then you can call it moderately strong, and that kind of explains what your life is like. Now, if you can imagine my sausage, there's a couple of candidates for probably being outliers. Would you agree? That guy way up there looks to me to be kind of separate from the main sausage. The main sausage is here. Where do you think the other one that I think is a candidate for being an outlier might be?
Down at the bottom. There's the one at 38.
Agreed. Now, let's pick that one at random. At a latitude of 38, the average of August temperature is 64. So I'm now going to leave that place and look for a latitude of 38, and it's San Francisco. So the weather in San Francisco is not what you would have expected it to be based on its latitude. Isn't it a little bit colder than it's expected to be? Now that can be all sorts of things. Couldn't that be El Nino or El Nina? I can't remember what the things are called. Couldn't it be something to do with just the mountains around it, or the wind coming in that causes its temperatures to go down or something? But there's probably some other factor that's contributing to that, and that's why it is an outlier. Now, in that picture that I had a few moments ago, which I'm bringing back, you will answer that question by picking one of those guys. Oh, shoot in space. No, you won't, because they did January, not August. Right? So they did latitude against January temperatures and not latitude against August. Well, that's easy fixed. There we go. There. So that's what latitude against their January weather is, right? So can you kind of keep that guy in your brain visually? Which one of those guys, oops, looks like him?
The second one over.
Right. So you're going for this one here? I agree with you. Now, that's a tiny picture and mine is a big picture. So don't you have to kind of like shrink it in your brain so that they're equal size to see it? What makes me agree with you is I tend to look for kind of features that I think stand out. Do you see this little guy here? This one right there? I can see that guy on my diagram that I can see. So I look for little, you know, guys that stick out, that look a little bit different. See how you have that big gap in this one? If you look at my data, let's bring it back again. Can you see that that point and that point have quite a big gap in them? And do you see on this one, there to there is a big gap, but the only other candidate would be this one. Do you see it doesn't really match? So all that hard work was just to pick this one.
Professor Robertson?
Yes.
Ashton just emailed me and he said that he's in the waiting room right now.
Oh, that was a while ago. I was like through 11:10. I was still in the waiting room.
Okay. But thank you. It's worth you doing that anyway, Sean. It's better you tell me than not. Because as you know, my issue with all the different windows, I don't actually get to see the waiting room once the thing goes, because I've got you lot in one window, I've got the thing you're looking at in another window, and I have my white screen going on as well. So you can imagine my desktop's kind of cluttered. So it's not a good excuse, but it's the best one I've got. And here is basically talking about, is it linear or curved? Oh, good. They said curved for a change. So they do use curved. They don't always call it curvilinear. Just a stupid name. So you get that. Now, sometimes in WebAssign, you get a question where it says, are there any cities that appear to be outliers because they don't fit the rest of the data? And then if so, which cities? So if we accept that this is our data set, we got to look for exceptional numbers, right? Now, if there was a town where my mouse is pointing, I don't know, can you see my mouse when I move on this thing? Right. If there was one there, I would say it was an outlier. If there was one there, it was an outlier. Do you know, I believe this one is an outlier. Now, it's in the same direction as the rest of the data. That doesn't stop you being an outlier, right? Would you agree that the data looks like it belongs here? And then there's a noticeable gap in that one. And that can very often be subjective as well, right? I think that's different enough to be an outlier. You might not. There actually is a numerical test for that, where you actually find a particular number. What's it called now? Oh, you won't, it's not in your course, but I'm trying to remember the name of it. It's a German name. I'll call it the Schumer number. And you find a Schumer number, and if it's bigger than 3, you're an outlier. It's a bit like 3 standard deviations away from the mean, right? You know, if you're 3 standard deviations away from the mean, you're an outlier, right? If your Schumer number is 3 or bigger, you're an outlier. So I would say it is, but it's debatable, right? Could be considered a choice. So let's look at our next one. Here's some data. Square footage and asking price. So that should be an easy one to do. I will go into charts, go into scatterplot, square footage, asking price. And I'll take that guy away. Oh, you see the data is not very, the association is not that strong. Would you agree? It's kind of going uphill, but you know, not very good. What about this guy way up there? Would you consider that an outlier? I hope everybody would consider that one an outlier. My previous one, we could argue about it. But I mean, look at it. There's a guy, and then, whoa, there's the next guy. If you are separated from the data set, right? It doesn't matter if you're separated in the same direction or some other weird direction, you're considered an outlier. Okay, I like that. That's good. Now, explanatory variable, right? In this relationship between square footage and asking price, which is the response and which is explanatory? Well, explanatory is the x's, response is the y. So whatever is on the x-axis is your explanatory variable, right? Whatever is on your y-axis is your response. Would you agree that the square footage of the house is the data you collect, right? It doesn't change, it is a number. But couldn't the asking price be different for different houses, right? So I don't know if that's a good way of saying it. I tend to look at it this way. The first column is X, the second column is Y. So the first column is your explanatory variable and your second column is your response. And 9 times out of 10, that'll get you. And I believe it was this picture or it was this one. I'm looking at my data right now and it ends up being that one. I'm not going to zoom back and forward. Can you trust me? It was that one. And there is an obvious outlier in the data. Yep, you're right, that one. Refer to the reasons for outliers. Well, I've talked about, right? If you're distinctly different from the rest of the data, that kind of thing. Explain which one of these is the reasons is the most likely cause for this outlier. So what does this data say? It's a square foot house that's 5,000 odd square feet, and it's going to cost you 1,600,000, right? Because that's 1,600,000, right? I think you call them, do you call them McMansions? Is that, I think I've heard that term. Right? A really, really big house is called a McMansion, right? So I think that data point is because there is a really, really exceptionally big house in this area, right? With over 5,000 square foot. And then there's a whole load of ones, and you can answer it your own way. And now we are moving back to our notes. Imagine that this story, that I'm going to use this pretend data, there is a line that you can pass through the data, right? It's given lots of different names, so I guess I'll give you them. It's called the regression line. Which is okay, I don't mind that name. It's called the line of best fit. I've seen that in textbooks. I kind of like that name, right? It's a line of best fit. I like that name. And the last one I do not like. It's called the least squares line. Now, the name that this book is going to use is regression line. So I guess that's the one I'm going to use, right? So if you have a scatter plot, there is a unique line. There is one line that is a better fit to the data than any others. Now, if you think about it, there are lots of possible lines I could do. So what does the best fitting straight line look like? Which is why I like that name. Well, would you agree it's the line that's closest to the most number of points? I mean, in English. And there's a really, really messy, ugly calculation that nobody does by hand. The computer does it for you, and they will come up with the equation of that line. And when they do, it will be called the regression equation. Now, since it's a straight line, straight lines are normally written like this. Agreed? That's what straight lines are looking like. They don't look like that in the context of these, because the x-axis is actually a thing. It represents age, and the y-axis is the weight. So you'll very often find the equation written like this. The weight of the animal is 5 times its age plus 10. So can we just pretend that that straight line was the line y equals 5x plus 10, but we would probably want it to be written this way. Can you see that this version of the equation of that line is much more understandable, because can't you now use this equation to predict how much a 6-month-old elephant or whatever the animal had decided this was, right? Because when you have an equation like this, can't you just plug and chug? So let's pretend that this is the equation of that line. And I would like to know what the typical age of a 3-month Scottish elephant is. Now, I'm picking Scottish elephants because the numbers are probably going to be really small. So you didn't know this, but Scotland has tiny little elephants that run around the Highlands, right? I made that up just so we can keep the data. So the weight of a typical 3-month-old Scottish elephant is 5 times 3 plus 10 which comes out as 25 pounds. Scottish elephants are really small, aren't they? Now, my data only goes from 0 to 6 months, right? But I could use it to predict what a 12-month-old elephant would be. Because can you imagine if that line just continued a little bit further and we expect the elephants to continue to grow, at least for a little while longer, at the same sort of a rate, wouldn't it be reasonable, not guaranteed, that you could use it to predict a 12-month-old elephant, even although you haven't collected data on that particular age? In this case, the weight then would be 5 times 12, add 10, and the elephant has now grown to 70 pounds. Now, these numbers are not a guarantee. If you went and found 10 12-month-old Scottish elephants, do you expect every single one of them to weigh exactly 70 pounds? No. Wouldn't that be the typical weight, right? Some will weigh 80 and some will weigh 63, but the average kind of weight. So this line is really giving you like the average typical weight for any given age, right? That seems reasonable. So it's not saying that elephant and every other elephant is going to weigh that. They're just going to say run about 70 pounds is a going weight for a typical elephant who's 12 months old. Make sense? And very helpful. So let's talk a little bit more about this equation. In the algebra world, let's return back to that for a minute. What do you call the 5 that's next to the x? It's given us a very special name.
The slope.
It's called the slope. And it's called the slope here as well. And we are very often asked to interpret, what does that slope mean, right? Does it have any meaning? Because sometimes it doesn't. And it has the following meaning. For every 1 month older the elephant gets, won't its weight increase by about 5 pounds? So if you're an 8-month-old elephant and you wait until you become 9 months, won't you probably be 5 pounds heavier? So in this case, the slope essentially says for every extra month, the weight increases by 5 pounds. Now, isn't this guy called the y-intercept? You remember that name? The y-intercept. And we will just call it the intercept, right? So what does the intercept tell me? What is the 10 in that formula telling me? Because it is actually telling me something that means something, right? It's just
the line goes through the y-axis where the line goes through.
Well, that's what it means here, right? That's visually, you're right. That's what it means.
Yeah, well, like that most elephants are born at 10 pounds.
Yes, that's the key. Exactly. Yeah. So in this case, the intercept is essentially, we would interpret in this story, we would interpret that as the weight of a new born animal. Elephant, whatever the story was. So do you see that equation, right? This regression equation can be used to predict the weight of in this case, elephants, right? But if you've got the equation, can't it be used to predict all sorts of things, right? So here's a totally new regression equation. And in this one, we're going to do the price at which a house is going to sell at is 500 times its area plus 50,000. Now, the area I mean is the area of the house in square feet, right? So a 2,000 square foot house, you put 2,000 in that. Right. So imagine you went to some place in California, because these numbers are going to be Californian numbers, right? You went to some place in California and you got a 2,000 square foot house. You know, how much would it cost me? Right? You can use this formula to predict the price of a house. Now, let's suppose I'm interested in that. What would a 2,000 square foot house typically, what was its price be? Well, it's going to be 500 times square footage plus 50,000. And that ends up being 1,050,000. And if you think that is expensive, you are correct. But me and my wife love watching house sale programs. And I have seen Californian prices, and I'm looking at it and I'm thinking, 900,000 for that 1,000 square foot piece of rubbish. They sell for that. I mean, I'm not saying all California does, but I bet you if you go to the closer to the beach or whatever kind of places, don't the prices get scary, right? So that is not an unreasonable formula. I could imagine if I was a real estate agent and I was trying to figure out how much somebody's house was worth, right? So they come to me and say, I want to sell my house. And you're going to say, well, let me look at the comps. You ever heard them say that? Let me look at the comps. Well, what they would be doing if they were mathematicians is they'd get as many houses near where that person is selling, right? Because area has a lot to do with the price, agreed? You know, if you're next to the water, it's going to be more than if you're miles away. And they make a little scatter plot and they come up with this equation because the software will do it. And then you go and say, okay, your house is 2,000 square foot. Yeah, that's your selling price. I think your selling price is that. Now, they might not make it exactly that. Do you know what they tend to do for psychological purposes? $999,999, right? And then they hope for a little bidding war and, you'll probably get that number. So you see, it can be used really quite useful. It's quite a useful thing to be able to create that. As I said, software does it for us. So that's 1 million. So let's look at the slope, which is 500. In the context of this question, what is that 500 telling me about the price of houses in California? I'll start it off for you. For every extra square foot of house, what happens to the price? And it goes up by $500. Does that make sense now that you can actually interpret the slope of an equation and it has a meaning? Not every time, but most of the time. In this case, it does have a meaning. Now, what's maybe less obvious is what the intercept means. And I don't think this number is very realistic, but it is what it means.
It would be the house or the land that it's on.
So if the house was useless, right, if you just had to knock it down because you're going to keep it, right, at least the land is going to cost you 50,000. I think that's unrealistic. I think it's probably more like $250,000 for the land before you even put the house on it. So if I was thinking about that, I probably would have called that 250,000, but it's too late now. And does that make sense that a zero area in the context of this question just means there's no house there? But there's still value there because there's still land, right? Even if the house isn't there, the land is, right? And in quite a few places, like I'm assuming in California, and there might be a thriving business for a company to buy ridiculously rundown houses that nobody's going to live in, just for the land that they're on, and the fact that you can build a house there, right? Because you've still got building permission, right? In fact, sometimes what they do is, don't they take a little house that's in a big lot of land, and even though the little house is quite good, they still knock it down. Because can you build a much bigger house in that same plot of land? And oof, up goes the price when you sell it. Now, I'm going to do a third one of these. And this time, we're going to do life expectancy. And the life expectancy is going to be 85, take away 2 times cigarettes that you smoke per day. So the life expectancy is 85, take away 2 times the number of cigarettes that you smoke per day. In fact, let's make it the number of packets. Packets of 20, right? Now, what this model is doing, first thing is, do you notice that the slope is negative? If I got that from some data, what I would be doing here is I would be finding out, I would be finding out the number of cigarettes, right, packs of cigarettes a person smoked. Now, this data would have to be collected after someone died, because life expectancy is the age at which we expect you to live, right? Or if you want to be a pessimist, the age we expect you to die at, right? So a number of doctors have collected information about various patients that they've got, and I'm sure one of the things they'd probably ask you is, how many cigarettes do you smoke a day? And this person says, oh, I smoke a pack of 10 a day, or I smoke 5 packs a day or something, right? And then they die, and you know that number as well, right? So can you imagine, you could collect that data, right? The fact that it's negative, won't it be going downhill? And doesn't that mean that the more cigarettes you smoke, the less you're likely to live? So if this was a true story, and you found someone who smoked 1 pack of cigarettes a day, then their life expectancy would be 85, take away 2 times 1. They would, on average, live to they were 83. Right. Not that every one of them lived to 83, right? Some get killed by a bus when they were 70. And some people, my dad, for instance, smoked his entire life. So he started smoking when he was 14. Different culture, different time. And died when he was 86. Right. So it doesn't mean every single person lives to that, because aren't there all sorts of other factors that kill you, not just smoking cigarettes? Your genes, your other lifestyle choices. But that's what that would mean. Now, if you could find someone who smoked 10 packs of 10, I don't even think this is realistic anymore, but let's pretend it was. It'd be 85, take away 10, and that would get you, they'd be lucky if they made it to 65. So can you see how you could use this data to make predictions on the life expectancy given how many cigarettes you smoke? So if you ever read articles or maybe heard something on the radio that says they've come up with some new data, and it says,
Mr. Robertson.
yes.
So I got an email 11:39. Mackenzie Lake is in the waiting room.
Okay, thank you. Where was I? Yeah, so you've got these. I've lost the place. So you've got this data, and that's it's good at predicting. So let's look at the two numbers. The intercept is 85. What is the intercept telling me in this story?
0 smoking, you'll average 85 years of life.
Right. So the life expectancy of a non-smoker. Agreed. That makes sense. It has a meaning, right? Now the slope is -2. In the context of this question, what does the -2 represent? So for every packet of cigarettes extra that you smoke, what will happen because of that?
2 years off your life.
Right. -2, it goes down. Are we comfortable about the intercept and the slope? They can have meanings, right? They tell you a little bit about what's going on, which brings me back to this, the thing that I get distracted. If someone came on the radio and says, hey, we've just discovered that for every cup of coffee that you drink a day, your life expectancy goes down by 3 weeks. So if you're a 10 cup a day guy, you're going to lose 30 weeks off your life. To which people who are addicted to coffees would say it's worth it, right? On the other hand, if someone comes out and says, for every pound weight that you are overweight, right? So for every pound overweight you are, you lose 1 day of your life. Then you might think, I'm 50 pounds overweight, 50 days of life, right? So you see that these kind of things, basically when you hear those in radio, do you know what they're telling you? They're telling you the slope of this equation. So if you're wondering where that number's coming from, it's just a slope. Any questions about that? I just want to do one more question from the homework and call it a day. Are we comfortable with regression equations and how they can be used? Yeah. Would you get it's much nicer than y equals 4x plus 10 if the formula has words? It looks more like a formula, doesn't it? And so it kind of makes a little bit more sense what you're doing with it. Right. In this question, the average weight, this is the regression equation, of men aged 18 to 29 years old. So this is men, and the average weight is -250 plus 6 times their height. And their height is in inches. Now, if you wanted to use this, right, to estimate what the average weight of someone who's 60 inches, then their average weight would be -250 plus 6 times 60. In this case, that's -250 plus 360. And the answer I get here is 110 pounds. Which I think looks a bit light, but it is what it is. I'm going to do one more of these. What do you think a 6 foot tall person is going to be? Well, won't they be a lot heavier than this? Because if there's more of you going this way, shouldn't you weigh more, essentially? So its average weight for a 6 foot person is -250 plus 6 lots of 72. I'm not going to do that in my head. So -250 add 6 times 72, and the answer we get here is 182 pounds. And so that's reasonable, right? You could do that. Now, The slope is 6. In the context of this question, doesn't that mean for every extra inch, your weight increases by 6 pounds? We agree with that? Every inch, 6 pounds. Now, I did say, and I'm pretty sure I said it every time, that most of the time, but not always, these two numbers have a meaning. Here is a situation where the intercept has no meaning. Would you agree? Technically, it's the weight of a person whose height was 0. But negative 250 pounds is totally nonsensical. Would you agree that that just doesn't make sense? So sometimes the intercept in particular has no meaning, right? It doesn't mean anything useful. Well, to finish off with, I should tell you that I am not overweight. Looking at this, I now know I am not overweight. I'm just the wrong height. Agreed? See, if I was 7'6", I'd be the right weight. You want to argue with that, David? Does that seem reasonable?
No, yeah, that it makes complete sense. I do have a
God,
question
you are
about,
gullible.
yeah.
Anyway, keep going.
I do have a question about the no meaning for the negative 250. Would that just mean that there's a strong association? Is that something you can conclude, or no?
No,
okay.
You can't conclude anything. It's just the numbers that came out in the formula. The reason why it is weird is that this data was only being used for adults in the range, 18 to 29-year-olds, right? So if you know the data is only being used in that range, you probably shouldn't use the equation with an age of 0 or a height of 0, right? What was an age? Yeah, you shouldn't use it with a height of 0, because that would be I'm not sure that would be a baby, wouldn't it? Because at least babies are 10 inches tall, right? So you shouldn't use it in a place where it wasn't designed to be used. But you do agree that I'm not overweight, I'm just the wrong height?
Yeah, that's not up for debate.
Oh, thank you. So when I see my doctor and she gives me the tut-tut thing and the conversation about I should exercise more, I should just come back and say it's been verified by science that I'm just the wrong height.
You should call it the Robertson theorem.
The Robertson theorem. Okay, say hi and bye-bye, guys.